Seems about right. Probably not going to beat Daryl, but that's really not surprising given the weather. Yeah. Okay. So you're going to need to turn the thing on.
Okay. Hi, everybody. Thanks for coming out. Great crowd tonight. So the first thing we're going to do is we're going to raffle off this, Eric, could you? Oh, there we go. This lovely ill space we've got. Okay, so our lucky winner is Daniel Cardish.
Ooh.
Okay. It's still on? Yes. Never used this one before. Okay, so everybody's used to my unrehearsed rambling introductions by now, if you've been here before. Who is here for the first time, out of curiosity? Wow. So only like half the people are used to it then. Thank you for coming out on this awful, awful evening for the first time. I mean, if you've been here before, you know these are awesome, and so I understand that you're going to come through horrible weather. But yeah, thank you for coming in this less than pleasant weather. And I'm sorry we're not going to be able to, once again, we're not going to be able to use the telescopes because they don't have the magic power to look through clouds. But hopefully next month, because Jupiter's now up and it looks great through the telescope and so on and so forth. So this is Astronaut number 42, and you've probably heard that recently scientists have made another step towards understanding life, the universe, and everything with the first detection, direct detection of gravitational waves. And tonight we have Elinore Roebber, who has been studying gravitational waves, just on scientific faith alone until now, and also by our strong understanding of gravity and so forth. So Elinore Roebber will take this away from me before I say anything else. Enjoy.
Thank you, Eric. Does that work? No, that doesn't seem to work right. Can you guys hear me? Okay, it's upside down, but I'll keep it like this just because it's working. All right, thank you everyone for coming out. I'm very happy to be here to tell you about what is one of the most exciting, I would say the most exciting discovery in physics and astronomy for a very long time. And that's the discovery of direct detection of gravitational waves. So probably a good first place to begin the story is about a month and a half ago when scientists at the experiment LIGO, the LIGO experiment, called a press conference and announced to the world that they had detected gravitational waves for the very first time. And of course, physicists everywhere went completely nuts. You can see here pandemonium at Caltech. This is really exciting. It's almost certainly a detection that's worthy of receiving a Nobel Prize. And even President Obama got in on the excitement. But to actually understand what's so cool about this discovery, first you have to understand what a gravitational wave is and why this is a really big advancement to have actually detected them. So to do that, we have to go all the way back to 1915, when Einstein first proposed the theory of general relativity. So the theory of general relativity is a mathematical theory that encapsulates our understanding of how gravity works. Everything that we understand about gravity, that balls drop when you let them go, all of that can be explained by general relativity, but a few more things are as well. And this extremely precise, very important theory has as its foundation a few kind of strange propositions from which everything else follows. And the first of those propositions is that space and time, which we're used to sort of being, everyday, very ordinary, unchanging facts of our universe, are not, and they're not separate. Firstly, they're connected in this thing that we like to call spacetime, which basically just says that space and time are related to each other and can be affected the same way. And secondly, space-time is not a fixed and unchanging sort of thing. It, in fact, is dynamic. It can be affected. It can be distorted. It can be changed. And so distortion in space might look like something like your geometry starts acting funny. Straight lines are a bit weird. You could get parallel lines going towards each other, going apart from each other. A distortion in time would act like your clocks are slowing down or speeding up in ways that seem strange. And from all of this really weird geometric idea comes out a theory of gravity. So this is Einstein's other famous equation, his slightly less famous equation. And it's the equation which governs general relativity. All of general relativity, or most of it at least, comes directly out of this equation. And what it does is it says that the curvature of space-time, this weird warped geometry of the space and the time that we live in, and also all of the mass, all of the energy, all of the stuff, all of the people in this room, these two things can affect each other. These two things are interrelated. And so you can read this equation in two different directions. The first is to say that mass and energy will cause warping in the space-time around them. So a picture that people like to draw is this: you have a bowling ball sitting on a trampoline or a rubber sheet, like this lovely image of the sun up here, where you have some sort of curvature underneath the sun, around the Earth, where the massive objects are distorting the fabric of space and time around them. And the second way you can read the equation is that the curvature of space-time, which you've probably created with massive objects, affects the way other things move. So it affects the way matter moves. If you drop a ball near the Earth, instead of it just going normal, if you just flick a marble across a trampoline, instead of going straight like it would normally want to do, it's going to be deflected. Its path is going to be bent by the gravitational potential well, by the curvature of the space around your massive object. And a really nice illustration of this, this is an illustration of what a black hole would look like with a backlight behind it. So the black hole's not doing anything there, it's just sitting. And we've got this galaxy moving around behind it just to show what this weird curved space-time looks like around the black hole. So you can see as the galaxy passes behind the black hole, you don't see what you would expect to see with just the galaxy. You see all of this light being refracted, being bent, being curved by the weird warped space-time around the black hole. And that's a statement that this space-time is curved, and so all of the light that's from that galaxy that's trying to come straight to you is getting bent, getting curved around. That's how you get this extra strange ring around the black hole. All right, so that was perhaps the world's shortest introduction to general relativity. But it should be enough to just get a sense of where gravitational waves come from. So gravitational waves were initially proposed in 1916, less than a year after general relativity. So Albert Einstein and Carl Schwarzschild came up with the idea that, well, okay, if we have massive objects that are warping space-time, then what happens if you move a massive object? Well, if you move that object, it's going to change the way the space-time is warped around it, right? The space-time is going to be shifting to accommodate that new motion. So they wondered, is there a way that you could create, something that you could create, if you have the right configuration of bowling balls moving exactly right on your trampoline, could you shake your trampoline? Could you create vibrations in the fabric of space and time? And so they went through some of the math and they found a solution and they said, yes, there is a way that you can create gravitational waves. You can create vibrations in the fabric of space-time. You can shake your trampoline just by moving things around on it, just by changing how you're warping the space and time. But of course, it's never quite that easy. So initially in 1916, they made this proposition, and they got a lot of backlash initially. So famous astronomer Arthur Eddington completely disagreed, others disagreed. Einstein himself was never completely sure, and 20 years later, he and one of his students tried to write a paper that said that purported to prove that gravitational waves did not actually exist, that the previous thing was just a mathematical fiction and illusion. And illustrating the benefits of peer review, the referee, when they submitted their paper, immediately found an error that said, nope, this theory is completely wrong. But there continued to be debate about this, lots of confusion, up until 1957, when the consensus in the scientific community finally agreed that yes, gravitational waves should be out there, but they didn't actually think they would see them. Oh, and if you found my explanation of general relativity confusing, then you can take heart in the fact that Einstein himself also found aspects of general relativity to be quite confusing. All right, so the modern understanding of what should be able to cause this sort of warping of spacetime, well, you need extremely massive objects. And the things that we think are going to be the most likely to see, to cause gravitational waves we would ever be able to detect, are very large, very massive objects in a very small area. And so the best contenders for that are black holes and neutron stars. These are commonly the remnants of dead stars. So a star gets to the end of its lifetime. If it's massive enough, it explodes, and whatever's left collapses down into a neutron star or a black hole. These are extremely dense. There's a lot of mass inside a very small space. So a neutron star, for example, is a star that's about the size of the sun, about the same mass as the sun, but the size is not. The size is about the same size as Montreal. And a black hole has more mass in a smaller area still. If there were a black hole the same mass as the sun, it would be about 3 kilometers in size. It would be much smaller. So here's an example of a simulation for how two objects going around each other. So we think that it requires 2 black holes orbiting each other, 2 neutron stars orbiting each other, to actually create these gravitational waves. So here's a nice simulation where you can see the 2 black holes dragging space-time around them and creating these little ripples. And as time goes by, you're going to see that the waves get stronger and stronger, and the black holes get closer and closer together. And that's because there's energy in the gravitational waves. And that energy has to come from somewhere, and it comes from the orbit of the black holes. So as time progresses, the gravitational waves go out, pushing the black holes closer together, till finally they merge. They spiral in together, collide, and they produce that huge burst of gravitational waves you just saw. But that was a 2-dimensional simulation. It shows where the gravitational waves come from. It comes from the orbit. But it doesn't show what a gravitational wave actually looks like. If you're sitting here and you see one go by, how would you even know? So the answer is what it looks like. What it looks like is it looks like a stretching and squeezing of space. Sorry, it says space-time there. It should be, this is actually just space. It just stretches and squeezes the space that goes by. So this lovely ring here is what would happen if you had a gravitational wave coming out of the screen headed directly towards you. It passes through that ring, and it squeezes the ring in one direction and stretches it in the other. And then it reverses, so it's stretching along the top direction and squeezing along the sides. And it keeps doing that. So here's a little more familiar example of the Earth. What happens to the Earth as a gravitational wave goes by? This is somewhat exaggerated. If it were actually to do this, we would all be dead. So you can infer that it's a little bit smaller of an effect than that. So since that one was an extremely exaggerated picture, I'm going to try to show you a little more realistic picture. But that's pretty hard because if we imagine zooming in, instead of looking at the Earth, the whole Earth being stretched and squeezed by a passing gravitational wave, if we imagine just, say, something about the size of downtown Montreal being stretched and squeezed, the amount that it would change in length as it pulls out or pushes in, the amount that it would change in length is something along the order of 1,000th of the diameter of a proton. So just to really point that home, think about downtown Montreal changing by this amount. So this is starting with a video starting with an atom, a hydrogen atom, if it ever loads. Yes, a hydrogen atom, and we're going to zoom in until you can actually finally see the effect. So this is nobody's really likely to die of this. Just to put this in perspective, another way of saying this is that if a gravitational wave were to come by and change the distance between us at Earth and the nearest star, that distance would be changing by less than the width of one human hair. 4 light years, 1 hair. Okay, so now that I've probably convinced you that this is impossible to ever see, let's imagine that we're really intrepid experimentalists and we're going to go out and look for this. So there's 2 different ways you can do that. The first is to directly look for the stretching and squeezing, in which case you need an extremely precise experiment able to detect 1,000th of a proton over 4 kilometers. Or, indirectly, you can look for how gravitational waves would affect something out there. Maybe you see the right kind of star system, maybe you see some other strange astrophysical system that tells you gravitational waves are here, gravitational waves have gone by, which is easier in some ways and harder in others. So the first attempt to search for gravitational waves came in the 60s, just a few years after scientists finally agreed that they actually are a real thing. And that was Joseph Weber with the Weber bars. So what these are large aluminum cylinders, and he's looking directly for stretching and squeezing of the cylinders. And he built the cylinders so that they're very, very sensitive, and they will resonate if they get compressed in just the right way. They will resonate like a wine glass with your finger rubbing around it will hum. So these bars will start to hum in response. And that hum is going to be very, very small because the effect is very small, but it should be able to be detected by this ring of sensors right around the middle of the bar that you see. And then in 1968, only a few years after he started, he claimed that he had made a detection. And everyone was really excited. But then other people started to go around and try to repeat his detection, and they weren't able to find anything. And in the end, it turned out that no, he had made there were some systematic errors. It was not a reproducible thing. He never actually found gravitational waves, which was very disappointing. The next attempt to look for gravitational waves came in the 70s when Hulse and Taylor, 2 astronomers, found a binary neutron star system. And this binary neutron star system was special because they could measure its orbit extremely precisely. And they knew, like we just talked about, they knew that 2 neutron stars that are going around each other should be emitting gravitational waves, should be giving off gravitational waves. And those gravitational waves, just the fact that they are going out and they have energy, means that the 2 neutron stars have to be getting closer and closer together over time. And so they measured this orbit very precisely over many decades and looked for this shrinking. And they found it. They found exactly what they would say. And so in 1978, they made the claim that they had seen gravitational waves. And then they continued to search for another few decades just to really hammer home the point. And then in 1993, they were given a Nobel Prize for this detection. So why am I here talking to you today about the first detection of gravitational waves? So the answer is that this is the first detection, but this is an indirect detection. They saw 2 neutron stars that are getting closer together. Yes, it matches what we expect about gravitational waves, but it wasn't the waves themselves. So the hunt continued. And in a few years later, in the 90s, starting earlier for the original technology, but the experiments were started to built around this time, are interferometers. And these are large experiments. These are kilometer-long experiments. They're L-shaped. They're looking directly for stretching and squeezing along the 2 different L's, the 2 different arms. Because remember, in the stretching and squeezing, you have one direction being squeezed and the other direction is stretched. And then it switches around. So if you have 2 arms, you should be more sensitive to something going on. And these are great experiments. They're more sensitive than the Weber bars. But unfortunately, they're not sensitive enough. And by that point, people had made good calculations of how strong we expect these signals to be. And so they didn't end up seeing anything, but it wasn't much of a surprise to anyone. And then the penultimate experiment looking for gravitational waves, before I talk about advanced LIGO, you may have heard recently, it was in the news the last couple of years, about cosmic microwave background telescopes. These are indirectly looking for gravitational waves produced by the Big Bang, or the aftermath of the Big Bang. And what they're looking for is they observe the cosmic microwave background, which is a field of light that's produced in the extremely early universe, only a few hundred thousand years after the Big Bang. And they expect, it is believed by scientists, that if gravitational waves are produced, which they very well could be, then they should create some sort of strange, very specific pattern of light on that cosmic microwave background. And so BICEP is a telescope, and several other CMB telescopes went out looking for this signal. And in 2014, you may have heard, there was a press conference, it was big news for a while, that BICEP claimed that they had seen this. And then after that, everyone else, got very excited, and they went out to try to confirm it. And after a few months, it became pretty clear that what had happened was it was mostly an effect of dust. So BICEP knew that there are other things out there that could produce light that looks similar to what they're looking for. They had some sense of how strong that should be, but it turned out that their estimates were much too low. And other experiments were able to actually measure the amount of dust, the amount of signal that should be produced. And it was nearly enough to account for all of BICEP's signal. And so in the end, we're unable to say that they actually detected anything. It's mostly dust. There might still be something there, but we can't actually make any claims. So finally, the experiment of the hour, Advanced LIGO. Advanced LIGO is one of the laser interferometers that we were talking about before. Its name stands for the Laser Interferometer Gravitational Wave Observatory. It's a 4-kilometer L. It's actually 2 of them, 2 in the United States, 1 in Washington State, 1 in Louisiana. And it's an upgraded version of the interferometers. They turned it off in a few years ago, and they've spent the last few years improving all of the technology, upgrading everything, taking all of the parts out, swapping them out for better things. And in 2015, last September, they finally turned on the experiment. And then now, just a few months later, they claim that they have seen stuff. And this is an extremely exciting result. And unlike some of the previous ones, this is probably actually it. We really believe that this is true. So since this is the experiment that's detected stuff, I'm going to explain to you a bit about how an interferometer works, how LIGO and its L-shaped arms actually work, how it measures the 2 different directions. So for gravitational wave, you want to figure out what is the length of your arms relative to each other. Because if a gravitational wave passes, you expect one arm to get longer and then shorter, and the other arm to get shorter and then longer. And so one good way of measuring this, because you can't just stick a ruler up, the ruler stretches and shrinks too, it's useless, but the speed of light always stays constant. So if you have 2 things that you want to measure and compare their lengths, if you send out 2 bursts of light at the same time how long it takes for them to reach the mirror, bounce off, and then come back, and you'll see that if they're the same length, they should take the same amount of time. If one of them is very slightly longer than the other, it will take that burst of light a slightly bit longer to come back. And so if you have a gravitational wave passing your experiment, you can just keep doing this over and over again, and you expect that one of your arms is going to look long for a bit, and then it's going to go away, and then the other arm will look long, and then it will go away, just like a gravitational wave signal passing should. But it turns out that that's not a very efficient way to build an experiment. So LIGO and the other interferometers work off of that principle. But what they actually use is a property of light called interference. So they have continuous lasers shining instead of individual bursts of light. But they can still time how long it takes for the light to go to the mirror and then return by using this property. And this property says that if you have 2 waves, so light is a wave, laser light is a wave. If you have 2 waves and they're perfectly aligned, and you put them on top of each other, you get what's called constructive interference. You end up with a light that looks quite similar to your original light, but twice as strong. If you shift those 2 beams of light so that they're no longer perfectly aligned, and instead the peak of one lines up perfectly with the trough of another, those 2 beams of light will be able to cancel each other out. And this sounds pretty preposterous when you say it works with light, but lasers are very special because they've got all of the rays perfectly aligned with each other. And it's something that you can see with water. So it turns out that it actually holds in this case as well. So once more, this is how an interferometer actually works. So again, this is the L-shaped experiment. You send off 2 pulses of light at the same time. In this case, one laser is split, bounces off of the mirrors, and then comes out at this detector. And you can see that depending on which alarm is longer than the other, you get more or less light at the output. So here it is again showing the actual waves. The actual waves go out, they bounce off of the mirrors, then they return to the beam splitter, and will recombine at the detector on the right there. And you can see it's set up so that normally those two beams should completely cancel each other out. You should get no light out at all. But if you change the length of one arm very slightly, that is no longer going to be true. And now those two beams of light will be able to actually add up, and you'll start to see something. And as the wave goes back and forth, it will keep changing, and so you'll see an alternating pattern of dark and light, and dark and light. And so that's a fairly simple picture, but it's very much how these interferometers actually work. But of course, it's much harder to build something that's going to be able to measure something that precisely, to be able to measure that 1,000th of a proton width. So I'm going to share a few of the really cool facts about the engineering. There's tons more. It's an entire talk's worth of material. So if you're interested, you can go to the LIGO website and learn more about it there. But first of all, the beam tubes, the tubes that the lasers travel down, they have to travel 4 kilometers long. And because it's a laser, it has to be perfectly straight. It has to be perfectly level. You can't have any deviation. It turns out 4 kilometers is long enough that they actually have to raise up the end of their beam pipe by a meter because the Earth starts to curve away underneath it. Also, because they've got this laser traveling through it, and it's a very powerful laser, and they don't want it to be scattered at all, they have to pump out the air. It needs to be an ultra-high vacuum. So they spent a long time pumping all the air out of these tubes, these 4-kilometer tubes, and the amount of air that they pulled out was enough that they could have inflated 2.5 million footballs just from the air in their experiments. Another cool thing is that the mirrors that they use to reflect at the ends and the front, these mirrors are extremely highly reflective. They're perfectly polished so that the lasers will never ever spread out as they travel along through the tubes, and they will continue to be focused. They are polished to a precision of atoms, and they have to be completely reflective so that they can't actually lose any photons inside of them. The laser that they use is 200 watts. It's strong enough that you could probably use it for industrial cutting. It's stronger than surgical lasers, so you want to be very careful when you start mucking around with it. And the way that they hang the mirrors, so you can't just stick it on the ground. They're really worried about vibrations, because if you're looking for a shift in 1,000th of a proton, if anything shakes your mirror, even a tiny bit, then that can destroy your signal. So they have this very complicated system that they've set up where they've got 4 pendulums, and they've got the mirror hanging at the bottom of it, and they've got a 40-kilogram mirror, so it's a lot less likely to actually shake around. And that mirror, that 40-kilogram mirror, is being held up by glass fibers that are 0.4 millimeters wide. 4 glass fibers per mirror. Okay, so that's a very short introduction to all of the really cool stuff in LIGO. They put 25 years worth of labor into developing all of that technology. But now, what does LIGO actually see? What is that pattern of light and dark that they actually see when the gravitational wave passes? Well, I'm not going to actually show the specific patterns of light and dark, but I'm going to show these characteristic waveforms, which we call chirps, which tell you how strong is the signal that they're seeing, and how often does it oscillate between being bright and dark in the signal. And it turns out that's closely related to what's going on with the binary system of black holes as it's passing. So here's a cool simulation showing 2 black holes going around each other. And right now you can see the weak waves coming out in this sort of spiral thing, and it's going to zoom in on the 2 black holes going around each other. So right now they're going very steadily. You have something that looks like the left-hand side of that cartoon, slowly going around each other, very steady, relatively weak waves. But as time goes on, they're getting closer to each other. They're spiraling towards each other. And as they spiral towards each other, the effect gets stronger. They create stronger gravitational waves. The waves get higher, they get stronger and brighter, and they get closer, they get more and more frequent. So you see changes more and more frequently. And then finally, as they get extremely close together, the video is now slowed down so you can watch the really cool merger. You're going to get this huge burst of waves right as the 2 black holes finally touch, and they form one black hole. And then they quickly relax down into its final state, and it stops giving off gravitational waves. So there you can see sort of the cross-section of those pink rings gives you the waveform on, in the cartoon next to it. And that's a chirp waveform, and that's a characteristic gravitational wave signature that LIGO's looking for. So you might want to know, why are these things called chirps? That's a bit of a weird name. And the answer is because the frequency of these waves, at some point somebody realized that it's the same, roughly the same frequency as the range of human hearing. So they decided, oh, it would be kind of fun if we translated this into something we can hear. What would it sound like? And it sounds like this. And that last little whoop is the two neutron stars merging. So that's the top wave up there. You can see it goes for a very long time before it finally merges. So two neutron stars merging. Two black holes merging might sound like this. Or perhaps like this. So they always sound a bit similar, but depending on how long it goes, how high pitched they get it towards the end, how low pitched they start out, you can figure out stuff about what's going on, what's causing that signal. So when LIGO finally turned on, when it started working, they decided that they were going to actually have an official opening, beginning to their observation session on September 18th, 2015. You know, all of the ribbon cutting and all of that. But right before that, a few days before, while they were finishing up their last tests, making sure that everything was working, in the middle of the night, between tests, this came by. And I'm going to play it for you. It's going to run a couple times. First, at the actual pitch, this is the actual data that LIGO got. And then secondly, it's going to go up in pitch a bit so that you can hear it a little better. It's sometimes hard to hear. Do you guys hear the chirps there? So this was astounding to the LIGO people, because first of all, this happened before they actually officially started their observations. They were expecting it would take years before they saw something that was this convincing. You can see that chirp by eye. You can hear it if you just play it. This is much, much, much brighter than anything they were expecting to see. They were expecting that they had developed this huge ream of algorithms that will hunt through their noise and search for these chirps. And this one just came up and it was just like, hi, I'm here. I'm a gravitational wave. And you can look at these signals and you can actually see a few differences in them. You can see that the Livingston one arrived a little bit before the Hanford one. If you look at the final merger, you can see the time is a little bit offset. That's 7 milliseconds to go 3,000 kilometers. And that tells us a little bit about where it was coming from, that it took that much longer to get to Hanford. And secondly, you can see that the Livingston one is a little bit upside down from the Hanford and a little bit smaller. And that's just because the two different L's are sort of pointed in different directions. They're oriented differently, so they catch different parts of the wave. So what did LIGO find with that chirp? It found two black holes, 30 times the mass of the sun, about, merging. So I'm going to show you a simulation of what that would look like if you could sit really close to it and watch, just from all of the light bending around them. And you might notice that there's no actually light being produced by this. If we pointed a telescope at this, we would never, ever, ever, ever see this, especially because these two black holes are 1.3 billion light years away. This is very, very far. And it's about to merge, and then you will see that it forms one final black hole, 60 times the mass of the sun, and then it's very still. And it's not much to look at in light. It looks kind of cool with the light around it, but you're not actually going to see it. This is what it would look like in gravitational waves. This is a 3D simulation now, showing all of the waves in orange. And it's a lot more obvious now. In the center, you can see all of the weird warping, the normal warping around the black holes, and the bright orange things are the actual gravitational waves. So it's a lot brighter now. You can see this much more strongly. And this is how we're actually able to detect it, is these things going by. As they get closer, you can see that the color is changing. That's saying that it's getting stronger. And then finally, that last green shell there, that was the two things merging. And that single bit of green light, that for a very short amount of time, the amount of power in those gravitational waves is 50 times the amount of power being produced by all of the stars in all of the visible universe combined, just in those green light waves. And that is the most powerful single event that humanity has ever witnessed. So that's pretty cool. But what did we learn from that? Okay, so this is just one thing. We learned, first of all, general relativity still works, right? This matches everything we'd expected. We found those gravitational waves. We found black holes. It looks perfect. We learned that black holes that are 30 times the mass of the sun exist. We had no way of actually being able to test that before. We thought maybe, yeah, it would make sense if they're there, but you can't really point your telescope around and look for these things. They usually aren't emitting light. We learned that black holes come in pairs. You can get two black holes together. Again, something that we had sort of suspected was true, but we had no way of actually proving before. And finally, we learned that since this thing showed up right away, we should probably see a lot more of them, which means that we're going to learn a lot more in the coming years about black holes and about their former lives and their deaths. All right, so some of you might be a little bit skeptical about this, since I just showed you a long list of experiments that claimed that they saw gravitational waves, and then it turned out they didn't. So why do I think that this is real? Why do the LIGO people think that this is real and just not another, false hope? So of course, it's always possible that it's not. Science, we do our best. We make mistakes like everyone else, but then we learn from it and we try to improve things. It's always possible it's not real. We can't prove it for 100%, but we think that it's very likely for several reasons. Firstly, the two different detectors that are 3,000 kilometers apart saw the same signal. They saw it at almost exactly the same time, the right time apart. It's pretty hard to fool that. Secondly, LIGO is extremely concerned about all of the different sources of noise out there. So they're very, very, very sensitive, right? So they have a bunch of different data that they're monitoring constantly. They monitor earthquakes all over the world. They monitor human activity, humans walking around near their detector, driving their cars, whatever. They monitor the weather. There was a very large lightning strike in Africa at the same time as this thing, and so they had to go through and be sure that it wasn't that. And turns out it wasn't, but you have to be sure. They worry about waves crashing on the beach. Neither of the experiments is anywhere near a beach, but so another reason that they're pretty sure about this is so they have all of the noise in their detector. They can monitor it. They understand it reasonably well. And compared to this signal, this one chirp, all of the noise in the weeks surrounding it is much less strong than that from the chirp. And so that they looked through this and they calculated that we would get something that looks sort of like a chirp that would be this strong by accident, just purely by chance, only once in every 200,000 years, actually less often than that. So it's probably not that either. Also, it looks extremely, very much like the chirp waveform that they would expect. And this is an important point because this is a difference between LIGO's detection and BICEP's claim. Because BICEP said that they thought it was there, but they knew that there was something else that could reproduce that signal. In this case, for LIGO, there's not a lot of things that could do that. It would be pretty hard to make that. And then finally, they had to also check the malicious injection theory. And so they went and they talked to anyone who'd been at the two experiments and sort of grilled them. And in the end, they were able to rule it out. Nobody had any particular motives or ability. But of course, we'll be completely convinced once LIGO makes some more detections and publishes them, and once other experiments are able to do so as well. So we found one gravitational wave from one event. So what's next? So it's not over now. This is not over. This is just the very beginning. So the next thing that's going to happen is they're developing a worldwide network of these experiments. Firstly, we have LIGO in the United States. We have Virgo in Europe, in Italy, which is currently being upgraded. It's one of the initial detectors along with LIGO. It's being upgraded, and it's going to be turning on this fall and starting to work, its first science run this fall. We also have KAGRA in Japan, which is being developed at the moment. It should be on in 2018. And then finally, right after LIGO, coincidentally, right after LIGO made their announcement, India agreed to actually build an experiment similar to that. And we will be discovering more things with LIGO, with Virgo, with CAGRA, with the Indian LIGO as well. This detection was only from the first month of the first science run of LIGO. It's not at full sensitivity yet. It's still being upgraded. It should be another at least 3 times more sensitive by the end. And they're currently upgrading it at the moment. It's off, but it's going to turn back on again this fall along with Virgo and do another science run together. So one source that we expect to see, in addition to more black holes, is we expect to see colliding neutron stars. This will be super exciting. This will be really interesting for our understanding of neutron stars, because neutron stars are these extremely massive things in a very small area. And they're so dense that we don't actually understand what's going on inside of the middle of a neutron star. It's something that we can't reproduce in the laboratory here on Earth. So watching 2 neutron stars hit each other, merge, and tear each other apart will tell us a lot about stuff. And here's a nice simulation video showing 2 neutron stars colliding and all of the matter that gets spread out as a result. So that's something that we can look forward to seeing a lot more of. And happily, it looks like LIGO and Virgo and friends will be able to see a lot of these. And then finally, who knows what else we could see? A lot of times, when you open up, you discover some new way of looking at things, you discover some new stuff. There's a lot of things that we might be able to see, but we're not sure yet, and we might still see some surprises. But LIGO and Virgo and all of those ground-based interferometers are not the end of the story either. It turns out that there's a whole spectrum of gravitational waves. Just like light comes in a spectrum, you have a whole rainbow of light, you have a rainbow of gravitational waves, ranging all the way from the ones seen by LIGO and friends, produced by black hole and neutron star mergers, the highest frequency gravitational waves, down much farther for a whole different range of colors of gravitational waves. And we have experiments either currently looking for these in all of these different wavelengths, or that will be built, we've got planned. So the next highest frequency would be probed by an experiment called LISA, or ELISA. Unfortunately, it's probably not going to be built until the 2030s. It's running into a lot of problems getting funds. But it would be a gravitational wave observatory in space. It's very much the same concept as LIGO, except instead of having 4-kilometer arms, city-length arms, it has 1,000,000-kilometer arms. That's arms about 2 to 3 times the distance between the Earth and the Moon. And it rotates around the sun, following the Earth in its path. So they're not going to just build this thing and put it up there and see that if it works at that point. They're currently working right now to try to see if they can verify the technology used in LISA before they actually fly it. Like LIGO, LISA requires extremely precise measurements. It requires extremely precise functioning of the hardware. So they've built a Pathfinder experiment, basically one of those individual satellites, that they've sent up to space. They launched it last December. It's currently out there. It started functioning on March 1st. It should take data for the next 6 months to a year, and then we'll be able to see whether or not LISA is going to be able to work. They're going to figure out what they need to do to fix it. So what's LISA going to be able to find us for astronomy? What's it going to be able to find? It's going to find a lot of things. This is actually an extremely exciting set of possibilities. So one thing it's going to see a lot of is white dwarfs and neutron star binaries long before they actually collide, before they crash. It's going to see these all throughout our galaxy. We're going to be able to map out all of most of the binary systems in our galaxy. These are all dead stars. White dwarfs are a bit like neutron stars, but less dense. We'll find a lot out about star evolution, star lives, star deaths. Another thing that it's going to be able to see a lot of are supermassive black holes. Supermassive black holes are a form of black hole that's different from the ones we were talking about before. Those black holes are usually produced at the death of a large star. It explodes. Whatever's left at the center will collapse down and form a black hole. These black holes, on the other hand, are 1,000,000 times or 1,000,000,000 times the mass of a sun. There are no stars that big. So where these things come from is something of a mystery. We see them usually one per galaxy. In almost all of the galaxies that we see anywhere. They're really huge. They're really, really powerful. We don't know why they're there. We don't know how they got that big. So they're a complete mystery, very possibly exciting because it could have ramifications for our understanding of the early universe. So one thing that ELISA might be able to see is smaller black holes, largish black holes, but much smaller than a supermassive black hole, falling into a supermassive black hole. And this video shows you somebody's example of one of these. So you can see a big black circle in the middle. That's the supermassive black hole. It's 1 million solar masses. Then in the sort of spirograph shape is the orbit of the smaller one going around it and falling in. And it will zoom in as you get closer and closer to the actual merger. Another experiment, this one is actually operating now to look for gravitational waves, is what's called a pulsar timing array. Pulsar timing arrays are a similar concept to LIGO, to LISA, to the interferometers, but instead of being experiments about the size of a city, about the size of a planet, these are experiments the size of the galaxy. So you can't anymore build a laser and put mirrors out at the end and see how that works. We can't go to the other end of the galaxy and stick mirrors there. So what they do is they use pulsars to measure the length, to measure their lengths, and to see if any gravitational waves have passed. And the pulsars sort of act like their mirrors. Pulsars are these really rapidly rotating neutron stars that are basically perfect natural lighthouses. You could set your clock by them. You can set your atomic clock by them. They rotate around every millisecond or so, and you see a bright pulse. And you can count them, and it should continue to repeat very steadily. So if you happen to see, you're counting all of your pulsars' pulses, and then you see that some of them are arriving late, and some of them are arriving early, and some of them are arriving early, and some of them are arriving late, then you can say, hey, wait, maybe we have a gravitational wave passing us. And you can keep monitoring that and look for gravitational waves. And it's a very similar concept to LIGO, but instead of having an actual laser, they're just looking at these pulses from the pulsars, looking for gravitational waves coming from far outside of our galaxy. And what gravitational waves are coming from far outside of our galaxy? Well, in this case, they're also interested in supermassive black holes. They're looking for what happens when you have two galaxies. The galaxies collide. The two black holes at the centers of the galaxies come together, and they form one of these binary systems. And they orbit around each other for millions of years, for thousands of years, before they finally collide as well. And while they're orbiting around each other, the pulsar timing arrays will look for them. And then finally, there could be gravitational waves produced just after the Big Bang. And all of these cosmic microwave background telescopes are still out there looking for them, despite the setbacks. It's still one of the most promising ways to see this. And we have hope that they will find them. All right, so I hope this talk has sufficiently convinced you that LIGO has made a first detection of direct detection of gravitational waves after 100 years. This is an important thing, not just because we've finally detected them, because we've finally managed to check off that last point on our list of things that general relativity predicts. This is important to us because we will be able to use it to do astronomy. We will be able to use it to understand the universe in a way that we were never able to do before. So for hundreds of years now, we've been able to point our telescopes out and understand the universe by looking at the light. We've been able to see the universe. Now that we've been able to detect gravitational waves, we can point our gravitational wave detectors out. We will be able to hear collisions of black holes, neutron stars, things we would never be able to see before. And now we will finally be able to hear the universe. So, thank you. Yes, right here.
When it says that the telescope can't detect black holes, couldn't it detect stars wobbling inside the black hole?
So that only, so the question is that telescopes can't detect black holes, but could they detect stars wobbling next to the black holes? That's true, but only if there's a star. So a lot of black holes we expect to just be out there on their own, maybe with another black hole, but no stars around them, and so we won't be able to see anything. Yeah, but for this case, it's just for regular black holes. The supermassive black holes we know are there partly by that effect. All right. Back there?
So I'm just curious about the two black holes that combined and that were later detected by LIGO.
Mm-hmm.
How are they able to determine where those were?
So they can determine how far away they are by looking at the frequency of the waves. They're not really able to determine where they are in the sky. They can use, what they know is that they know the difference in time between the two detectors. They know the differences in the patterns measured by the two detectors. And so they can take a big streak of the sky and say it's somewhere in there, but they can't be more precise than that. Once they have more detectors, they'll be able to know more closely. Do you have a question? No, that was good. Anyone else? Yeah, over there.
Is there a lower limit
Sorry.
to the amount of mass that carbon dioxide?
In theory, no, but in practice, you're not going to be able to see gravitational waves that are from anything small. So these are the biggest things that we can, the thing that we can see, these are the biggest things, first of all. Anything produced by, say, us moving around is going to be completely impossible to ever detect. In the red in the back? If you have two different waves at the same time? So in this, for LIGO, we don't expect that to happen very much until it's starting to detect things all the time, because it was a very short waveform. It was only a few milliseconds. But if you have multiple things at the same time, then it's going to end up having an effect that's similar to the interference I was talking about before. So you're going to end up with some sort of weird added thing. And if you have many different detectors, it will be easier to actually piece that out and figure out what the different things are. Okay. Yeah, right there.
How long does the collision process last?
Sorry?
Are you guys able to know how long does the collision process last?
How long does the collision what?
Like when they collide?
Yeah.
How long does it last for them to collide together?
That they can just see by looking at the last little whoop bit. That tells you how long they took for the collision.
So they know from the beginning when they got close together,
Mm-hmm.
how big each other sort of
Yeah. So the question is how they know how long the collision actually lasts. And the best way to say is to look at this image here where you have this actual waveform. When it looks like sort of a regular wave going up and down, that's when the two things are going around each other. When it suddenly gets really bright and you have a peak and then it goes away, that is the actual collision itself. So looking at how long it takes, how long that sort of bright peak time is, that will tell you about the same length it lasts.
And do you know when the collision happened?
What do you mean?
Like when in time it happened?
Yeah, so we know that gravitational waves, so the question is, do we know when the collision happened? And the answer is that gravitational waves go at about the same speed as light. So they happened 1.3 billion light years away, so we know that it happened a billion light years ago as well. All right, in the blue there, or the green?
How will the discovery of gravitational waves affect the research and the hunt for gravitons?
Sorry?
How will the discovery of gravitational waves affect the research and also the finding of gravitons?
Okay, so gravitons technically should be the same thing as gravitational waves. It's the sort of the particle of gravity, just like gravitational waves are the wave version of it. I don't know if anyone's actually looking for gravitons in a particle physics context at the moment, though. But theoretically, they should be the same thing. All the way in the back there?
Why is it only at the surface in space and not space-time?
Come and ask me that later. It's complicated. The question was, why does it only affect space and not space-time? Yeah, right here.
So when LIGO is doing its test and trying to detect the gravitational waves,
Yeah. Yeah, so it's true they can't actually turn their detector off and look for non-gravitational waves happening. They can't understand what their detector is like when it's not on. So what they basically just do is they study their noise very, very carefully. They understand their noise very carefully, and they take the time streams for their two different detectors and shift them in time and use that with a bunch of algorithms that they've developed in order to see if they can characterize what it would look like without gravitational waves.
So basically, there's no negative control.
No, it's not possible. Yes, right there.
The LIGO event was very short. Do
Mhm.
we expect all events in the future to be that short? Or do we have hour-long events?
Yeah, so that's a good question. The question is do we expect all events to be that short? The answer is no. It depends on what kind of system you have. So in the chirp I played you for the two neutron stars, it takes a very long time for them to actually merge. The more massive your objects are, the faster they're going to merge together. And so the shorter the actual thing will be. And also, for more complicated systems, like the one I played for you for the ELISA with a supermassive black hole and a stellar mass black hole going inside of it, those will take a very long time to actually merge, just because it's a complicated system. Yeah?
Do gravitational waves have different speeds through space and through objects?
No, they should basically be always traveling at the speed of light. So technically, they might have a slightly different speed, but it's going to be the matter is going to slow them down very negligibly. In the back in black, I think.
Yes. Are there still untested predictions for general relativity, or have you basically checked everything?
No, we haven't checked off everything. We don't understand the nature of black holes very precisely. We haven't been able to look at black holes right next to the event horizon. So that's something that people are still working on doing. But many of the predictions of general relativity have been checked. Yeah, right there.
How do you relate what the LIGO detect on these waves? Is there a way to convert that to like something observed in a telescope, or is there, and how can you prove that you're actually
Right.
detecting a black hole in
Right.
a not
So in this case, so the question is, how can we compare LIGO's detection with something that we could see with a telescope? Can we actually verify that something happened? So yes, LIGO has this program set up where every time they see something that might be a gravitational wave, they basically send out a really fast email to a bunch of different telescopes who go and point their telescopes in that direction to look for something. In this case, they all did, and basically all of them found nothing. One experiment found something that is a little bit, it's unclear if that's actually it. And in this case, you don't actually expect two black holes colliding together to produce any light at all. So if we have a neutron star, then we would be able to do that. And it's very much to hope that that will happen soon. Yeah, in the back, center. Yeah, you.
Does the orientation of the LIGO affect the way the signal is perceived?
Yes.
So would it be stronger depending on, say, if the Earth is spinning at one position than the other, or at a different relative position?
So I don't think this.
Is the signal always pretty well the same that comes from these collisions?
Yeah.
Depending on where we are.
Yeah, so the signal is different depending on where we are compared to the plane of the collisions. So you have the two black holes going around each other in a plane. So if you're looking at it face on, it looks one way. If you're looking at it edge on, it looks differently. So mostly.
If we're in the wrong orientation, we might not see it.
Yes, possibly. That's another reason to have multiple detectors. So if they're all in different orientations, one of them will definitely see it. Several of them should see it. Yeah, right there.
In the spectrum of gravity waves, which we only can see part of it now,
Mhm.
was this event sort of the brightest one that you sort of predicted, or are supermassive black holes emerging brighter?
Yes, yes. So the question is this the brightest? Is this the brightest signal you'd expect to see in the spectrum? No, this is actually not. This is one of the brightest things you'd see in the LIGO spectrum. But it turns out that as you go to lower frequencies, you have bigger things. So supermassive black holes merging will be much, much brighter than stellar mass black holes merging. So this is actually much dimmer than other things you would see. It's just harder to build the other experiments. In the back there?
Any idea if this event was
It was far outside of our galaxy. It was a billion light years away. Our galaxy, the next galaxy is only a million light years apart. So this is many, many galaxies away. Yeah, over there.
During one of the slides, we had different categories of gravitational waves require different experiments. But so since to find the ones that have lower frequency, we need like bigger experiments. But then why can't we use the bigger experiments to find easier the high frequency? Like if it's just bigger, shouldn't that mean it's more sensitive and therefore we find like
The brighter stuff?
you know what I mean?
I think so. So, yeah.
That allows to find experiments on this side easier.
Yeah, so the answer is the size of the experiment actually doesn't tell you how good it is at detecting things. The size of the experiment, at least when you're comparing 4 kilometers to 1,000,000 kilometers to 1,000 light years, that size of the experiment tells you what wavelength you're looking for your signals. So it's not sensitive to ones at higher frequency at all. Yes? This event? Yeah, the one that LIGO saw. Yes. Okay, that's actually a great question because the answer is yes. ELISA could have detected the event that LIGO just saw. It would have seen it about a month or a few years before LIGO. So what it would have seen is it would have seen the two black holes at a farther separation, slowly getting towards each other. Then at some point it would have stopped seeing it. And then a few weeks later, LIGO would have actually seen the same signal. Huh? ELISA, it won't be launched until 2034. Unless somebody sends them a whole lot of money. Okay, a couple more questions in the orange there. Sorry.
If gravitational waves are emitted continuously, then after the first gravitational wave, we detect them continuously.
So you're saying, should we be able to detect them continuously if they're being emitted?
Then we continuously detect them after the first detection.
Oh, okay. So a single binary system will be emitting waves continuously up until a point when it actually merges, and then it stops emitting waves. So what LIGO can do is it can see the last very short amount of the last maybe few seconds of some system's life, and then it doesn't see any more. And then it has to wait around until the next system decides to collide. And so it won't see anything between those two. Does that answer your question? Okay. Okay.
What does Virgo stand for?
I don't think it actually stands for anything. It's a constellation. All right, and you in the front for the last question.
For like gravity waves, if one were to hit the edge of the universe, would it bounce back?
Okay, so
If you have like a bucket of water,
yeah. No, I understand what you're asking.
then a ripple forward and then ripples back.
Yeah.
Would it be the same if a gravity wave hit the edge of the universe?
Okay, the question is if a gravitational wave hits the edge of the universe, will it bounce off? So the answer to that is that we don't know of any edge to the universe. There's an edge to the universe that we can actually see, and that just tells you how long has it taken for light to get to us from the edge of the universe. So there's no actual physical edge there, so it's just going to keep going. All right. Any other questions? People can come see me afterwards.